So r dot square plus l square by r square, and then you have 1 minus gm by c square r, okay, minus 12 gm by r is equal to c square minus 1. So this is the equation we had derived already. This is the equation which describes the radial motion, okay, of particles, of massive particles. Now let's take this thing. Okay. So let me take the radial motion. So when I take the radial motion, that means phi is constant, or in other words, this phi dot is equal to 0. Clear? So we are equipped with 3 equations. One is the equation for t dot equation, remember? Another is an r dot equation, and third is phi dot equation. And theta dot equation is not there, clear? Because okay, so because we are in the fixed plane, fixed theta plane, or we are actually dealing with the equatorial plane. Okay. Now when I consider the radial motion, okay, so that means there is a radial infall of a particle towards the massive object. Okay, so what is phi then? What is the phi dot equation then? So there will be no motion along phi. Clear? So think of a particle. Okay, you throw a particle from here to the surface of the earth. What is the phi coordinate? It's not changing at all. Okay, so there is no phi velocity kind of thing. Okay, so you are having only the radial motion. So in that sense, I am having phi dot equal to 0. When you are having phi dot equal to 0, what will happen to this h? It's equal to 0, because h is what? So if you remember, we are having this r square phi dot that's equal to 0 is equal to h. So it implies h is equal to 0. Okay? So it implies 0. So now let's write this equation. So then I am having this r dot square, okay, is equal to, so let's take this factor on this very side. So it is c square k square minus 1 plus twice gm by r. Okay, so let's call this as equation 5. Okay, so now let's differentiate this very equation with respect to our parameter. Since we are dealing with the time-like geodesics, okay, for time-like geodesics, this parameter that will parameterize the curve, the trajectory, is the proper time. So let's differentiate this with respect to the proper time. Okay, so it will be twice r dot, so r double dot. Okay, so this is a constant, this is equal to 0. Okay, minus twice gm by, okay, what it will be, r square, then it will be r dot. Okay, so which gives me what, r double dot is equal to minus gm by r square. This is a very profound result. Okay, so we are considering a free fall of a particle. Okay, so Mushama, under Schwarzschild geometry. Okay, so what is the trajectory? How the trajectory looks like? How the trajectory looks like? So it is like this kind of thing. So it is simply the Newton's law of gravitation, is it? Or the acceleration due to gravity. But there is a catch in this very formula and the Newton's formula. So although the results look like identical, but the interpretation is different. Okay, the first point is that this r is not the distance between the particle and the center of the mass. Okay, the test particle you are taking and the massive object which creates the our gravitational field. This r is not the distance of separation between the two. In other words, this is not the coordinate distance. Okay, so much. And other key difference is that this this acceleration, what we call for the time being, so this is actually the differentiation with respect to the proper time. It's not with respect to the universal time in the Newton's law. Newton's laws has a differentiation with respect to the universal time. Clear? So these are two key differences. Okay, the coordinate distance. Okay, the coordinate Radial distance, or the distance of separation between two objects, is related by the metric. Samusha, in our geometry, it is related by the metric, but it's not related by the metric in the Newtonian gravity. Got it? Okay, so let me put it. Okay, so it should be the coordinate r is not a radial coordinate, or the radial distance, I should say a radial distance, and dots indicate derivatives. With respect to proper time, then universal time in Newtonians. With respect to then universal time in Newtonian mechanics. Okay? R, which is the radial coordinate. R is a radial coordinate. Okay? It's not the radial distance. There is a difference between the coordinate and the distance. Okay? So R, which is the radial coordinate. Okay? Is related to radial distance. Okay? Through metric. Got it? So now let's take an example. So now if I have okay, so let's look at this equation 5. So let's draw. So let's take an example, and you are having some massive object at rest at r equal to r. Okay, so draw at r is equal to r, which is r is a fixed distance. Okay, so you are having some, let's say, a massive object at some distance, at some radial coordinate, which is equal to r. Okay, at this very point you drop a particle. Okay, so much even. Okay, so what will happen? So let me drop this very particle from this very fixed position. Is it? What is happening? What is the interpretation from the Newtonian mechanics of this mere motion? So it says, so whatever is the loss in the potential energy is equal to the gain in the kinetic energy. When you drop a particle in the gravitational field, so the loss of potential energy implies what? The gain in kinetic energy, or the loss in the kinetic energy gives you what? If you throw it upwards. Okay, if you throw it downwards, it means you are losing the potential energy. If you throw it upwards, you are losing the kinetic energy. Clear? So let's look at that kind of result, whether we are able to derive that kind of result. Okay, so at r, okay, so this is, so drop a massive particle from rest at r is equal to r. R is a fixed distance. Okay, now tell me, so first I will try to calculate what is the constant, this k at this r. Samajh everyone? K is the unknown here in this very equation, although we are having the value of k in the asymptotic limit we know, so that's equal to 1. So when r tends to infinity, this k tends to 1. This I have given the interpretation. Actually, k is related to the energy of the particle. So when you go in the asymptotic limit, so this k turns out to be the 1. Okay, so now if I take this r dot, what will be this r dot? So let's substitute r is equal to r in this very equation. What will be the r dot? 0, because it's at rest at that height. Clear? So Samusha, so in other words, I will be having 0 equal to c square k square minus 1 plus 2i gm by r. So what will be our k square? K square, anybody? 1 minus 2i gm by c square. Is it? Is this the k square? Isha? Okay, good. So now let's substitute it in equation 5. Okay, so which implies, so I'll be having this r dot square by, let me write half, because there will be 2, this factor of 2, since you are having k square minus 1, okay, so that will be simply 2 gm by c square r. Okay, c square and c square goes, समझो, k square minus 1 I need to figure out, it's simply 1 by c square, like this thing, so it will be so that 2 I am taking here. Okay, so what I will be getting, anybody? Gm into 1 by r minus 1 by r. Okay, so what this object is, anybody? So Gm by r is actually potential energy at r, is it? At small r, and this is the potential energy at capital R. समझ आओ? So what this is? This is actually the difference of the potential energy. What it is equal to? Kinetic energy. If I multiply this by some test mass m, okay, so you are having m here, so this will be what? Kinetic energy, and this is actually the potential energy. समझ आओ? So that means at when a particle falls off what? In a gravitational field, so what happens? So the loss in potential energy is equal to gain in kinetic energy. Okay, got it? Okay, so this so this is the same kind of formula what we are having in the Newton's theory. Okay, but only the difference is what? What is the difference? This differentiation is this r dot is actually dr by d tau. It's with respect to the proper time of the particle. Got it? Not with respect to the universal time. Clear? Okay. So now let's look at the general case. So if you have any question, so okay, so let's look at the general analysis. So we will drop a particle at infinity. Okay, so infinity means the observer. Okay, so let's think of an observer who is at rest at very far off distance. Okay, so let's look at a general analysis for an observer at rest. So this observer is actually the particle. When I say the particle, it means the massive particle, object carrying the mass at okay. So in this case, our constant k is equal to 1. Okay. समझ आओ? So therefore, from geodesic equations, now tell me, okay, so you are having an observer who is at rest at infinity, clear? Now what is the time? Okay, the time that is measured by this very observer, okay, in its own frame, that's also the proper time, but that proper time we call as the coordinate time. Suppose this observer looks at another particle which is falling in this very space time, clear? And he will measure the time for that very falling observer. So the time that will be measured by this kind of observer will be as the coordinate time. Got it? So this is very important. So how many of you have gone through this coordinate time and proper time? I asked you last time. Okay, so let's do the analysis. So what are our geodesic equations? So these are 1 minus 2s mu by r p dot, that's equal to k, that's equal to 1. So which implies, so dt by d tau. So since t dot means dt by d tau, okay, so So that's equal to 1 minus twice mu by half. Okay. So what this will give me? So this will, okay, if I integrate this very equation, so this will, okay, if you look at this very equation, this equation gives you the relation between what? The coordinate time and the proper time. Tisha? Got it? Okay. So now let's take the another relation. So that equation 5. Equation 5 had what? That r dot square is equal to c square into k square minus 1 plus twice gm by r. Is this equation clear? And what is, okay, so we use the parameter mu is equal to gm by c square. Is this the case? So what will be gm? It is mu c square. So since k is equal to 1, what I am having? So I am having this r dot square, that's equal to twice mu c square by r. In other words, or I can write this thing r dot, so that's actually dr by d tau, so that's equal to plus minus, okay. So let me write plus minus first. So it is twice mu c square by r raised power half. Okay. So since we are looking for a particle which is an infalling particle in the geometry, is it? So when I am having an infalling motion, so what is the velocity vector? So since this dr by d tau is simply the velocity, is it? So what will be the slope? It is negative. So let's take the infalling observer, only the negative side. So there will be two signs. One will be the velocity of an outgoing particle, another will be the velocity for what? Ingoing particle. Since we are looking only the ingoing motion, so you are having here, let's say, a massive object. So you threw a particle at rest from infinity, so it will be moving towards that very mass. So it is an infalling observer we are looking at. Clear? Okay. So this will specify the trajectory of the particle. Clear? Got it? Because this is dr by d tau. From this very equation, okay, I can calculate the proper time as a function of r. Can I calculate? So what is our aim? Now let me try to put this way. Our aim is to figure out how much proper time it takes for a particle to cross the surface r equal to 2 mu. Or how much proper time it takes for a particle to reach from an infinity or from certain distance to another distance in this Schwarzschild geometry or this Schwarzschild space-time. Clear? So let's say there is an infalling particle from, let's say, r equal to r naught. So this is our initial position. Let's say that's at t tau equal to 0. So let's calculate how much proper time it takes to reach r equal to r at tau is equal to tau. Got it? So we'll try to figure out this proper time. Okay, if I know the proper time, that means I can figure out what is the trajectory of the particle itself. Okay, from this very equation, I can calculate actually what? Coordinate time. How much coordinate time it takes in terms of the proper time. Proper time I will be knowing from that very equation, and the coordinate time I will be knowing from this very equation. So let's try to integrate this very equation. Okay, so which gives me, okay, so let's figure out this thing. So it's r raised power half dr, that's equal to minus twice mu square raised power half d tau. Okay, so let's integrate this very equation from where? From r naught to r. Okay, r raised power half dr, that's equal to twice mu c square raised power half from some 0 to tau. So where r naught is the radial coordinate at tau equal to 0, you start from somewhere, and r is the radial coordinate at proper time tau. Got it? Okay, so let's integrate it. So once you integrate it, you will get. So Everybody is following what we are doing? Okay, so which implies I can calculate this tau. So what is the integration of r raised power half? It's r raised power 3 by 2, is it? So that means factor of 3 by 2 will come. Okay, so when you put it in terms of tau, so it will be 2 by 3 like this thing, r naught cube by twice mu c square. This means r naught raised power 3 by 2, huh? Okay, and twice mu c square is having the root, huh? Okay, so minus 2 by 3 root of r cube by twice mu c square. So this is a very important formula. Okay, so this is the proper time experienced by the particle from r equal to r naught to coordinate radius r. समझ आओ? So you are having an observer who is under a free fall, let's say. So from the position r naught to r, okay, during this very free fall, he will observe how much time? So the time that will be measured or observed by this very observer who is under free fall is this proper time. Okay, so that much of the proper time arises there. Okay, so now there is one important point here. Look, so now let's say, so what is our, if you look at the matrix itself, so our matrix is like this thing, Gij something 1 minus twice mu by r. Okay, then you are having 1 minus twice mu by r raised power minus 1. Okay, r square and r square sine square, the original thing, yeah, containing all these factors. So this is multiplied dt square, dr square, d theta square and d phi square. I have written just to the matrix, yeah? So we can write the line element as well. Now let's say if you take r equal to 2 mu, so what happens to this very object? This becomes 0. So we have no problem here. Now when r goes to 2 mu, it's 1 by 0, it's infinity. So it appears as a singularity, but it's not actually a singularity. Okay, it's what we call as a coordinate singularity. Okay, so it is because of our the system of coordinates we are using, so it appears as a singularity, but exactly it is not a singularity. Okay, so now let's, okay, I will discuss this object later on. For the time being, let's say I am having a region. Let's say you are having this kind of mass. Okay, let's assume this is our r equal to 2 mu. So it can, this can be on the surface of the body itself, it can be within this thing, it can be outside. So we'll so we'll calculate. Let's say this our r equal to 2 mu. Now, if I look from the line element, when the particle reaches the r equal to 2 mu, it blows up, is it? So there appears as this kind of singularity. There is a problem. Okay, but it's really not a problem. Look at this thing. So when r goes to what? How much? 2 mu. So let's say r goes to twice mu. So what is happening? So this object is finite. So that means for a particle who is under a motion or an infalling particle towards a massive object, when it crosses r equal, so it takes actually finite proper time to cross this very region. So nothing happens in its own frame of reference. Got it? So you can say it's okay. Now let's try to calculate what is the coordinate time. The observer who is at infinity, let's say you are having an observer here who is at infinity. Okay, so he will be watching this very observer crossing this r equal to 2 mu. Now let's look at how this r equal to 2 mu looks like for this very observer. Okay, what is the amount of time, okay, taken by an observer from the perspective of this very observer to cross this r equal to 2 mu. Samajh aao? You got it? So let me write it. So and one more point, if I take, let's say another thing also. So when r tends to 2 mu, tau is finite. Okay, it's finite. It does not go to infinity, is it? Not that so much. If you look at here, r equal to 2 mu. So this is actually a finite thing, huh? So it does not go to 0. Okay. Now also r tends to 0. That means towards the center of this very object, or the center of this very dotted circle. Let's say this is r equal to 0. So what happens when r tends to 0? This tau goes to what? 2 by 3. So r naught cube by twice mu c square. So that's also not equal to 0 or so it's also the finite. So that means it takes finite proper time for an infalling observer to cross either this r equal to 2 mu or to reach the point r equal to 0. So we'll see this r equal to 0 is actual singularity in our space time. Okay? But it takes the finite proper time. But let's look at from the perspective of the observer who is sitting at infinity, or the asymptotic observer. And the time that will be measured by this kind of observer is actually the coordinate time. So now let's look at how much coordinate time it takes to reach an observer to this surface, r equal to 2 mu. We'll see, in the next lecture, this r equal to 0 is actually the actual singularity, what we call it the black hole singularity. Okay? And this r equal to 2 mu will simply give me the event horizon of the black hole. So that we'll see in the next lecture. But keep in mind, so the proper time is the finite for the infalling observer. Okay? So now let's look at this dr by okay, so let's look at the coordinate time. T. So this is the time measured by the observer at infinity in its rest frame of reference. So okay. So how I can calculate? Let me take this dr by dt. So this I will write dr by d tau and d tau by d. Can I write it? So I can integrate this very equation to figure out this t in terms of r, and I know the formula for dr by d tau as well as d tau by dr. So how much is that? So let's write. So it's minus twice mu c square by r raised to half and 1 minus twice mu by r. So this object is this thing, d tau by like this thing. So what is okay? So you can now integrate. So you are having like this in r raised for half divided by 1 minus twice mu by r. Okay, dr, that's equal to minus root of, so this object is a constant d. Okay, so now you can take r here. So just integrate. This is a very simple integral. Just rearrange the terms. Take r here. So let me put it in the simplified fashion. Then you integrate it. Okay. So what is that? So it's r. So r will go up. So it is r root of r divided by r by 2 mu minus 1. What I have taken out? Twice mu. Okay? Is equal to minus 1. Twice mu 6. Okay, just make the partial fractions here. So put r by twice mu minus 1 here. Huh? Okay, so go for push. Go for push. Okay. Okay. So this is this r. Okay. So now integrate from some r naught to r from 0 to tau. Okay. So this is a little bit lengthy integral. The value of this very integral. Okay. So after integration you will get t. Okay. Sorry. So what will get? So it is 0 to t. It is 0 to t. So this r naught is actually the radial coordinate. When the observer at infinity measures its coordinate time to be 0. समझ में? While he starts. So that means the infalling particle starts its journey at where? R naught 0. समझ में? And to the point R t. Got it? So let's say, so it will be something 2 by 3 like this, root of R naught cube divided by twice mu c square minus root of R cube plus 4 mu by c root of R naught by 2 mu minus root of R by 2. This is a very simple integral, huh? Just do it. It's x root of x divided by root of x minus a. समझ आओ? Sorry, divided by x minus a, not root. Plus, so there will be actually logarithm term, which is very important. Like this, the root of r by twice mu plus 1. Okay, so here you have to use log of a minus log of b, that formula, because you have to evaluate it at 2 points, at r naught and r. समझ में? That's why there I am clubbing everything here. So it's root of r by 2 mu, so minus 1. So it is the first term, then you have to evaluate it at r naught by twice mu plus 1 divided by root of r naught by twice mu minus 1. Okay? समझ आओ? So this is the formula for the coordinate time. So now let's look if r tends to 2 mu. Okay, since r is the final distance, r naught is the initial distance. Okay, so we have nothing to do with the r naught. Okay, r is the final point. So let's take r crosses the 2 mu, or r reaches the 2 mu. What will happen? So when r tends to 2 mu, okay, so it diverges actually. So when r tends to 2 mu, so that means when it reaches to the event horizon, okay, so what happens? So forget about these things. So you are having this very object, so it becomes 0. So it's 1 by 0, it's an infinity quantity. So it means, implies t tends to. So what does that mean? So it's very important result. So this will help us to understand the black holes. Okay? So what is t? T is the coordinate time. It is the time measured by, so let me write, so this is r equal to 2 mu and this is our r equal to 0. So an observer is here. Okay? He measures the time t and you are having an infalling particle from here. Let's see. So this observer who is sitting at the infinity, he measures, it takes an infinite time for the particle to cross what? This event horizon. So it means for this very observer, the particle never crosses this event horizon. But if I look from the proper time, the trajectory of the particle itself, it crosses. So what does it mean? It appears that, so this kind of object, when you are having this kind of scenario arising, so nothing will come back. So when nothing reaches to this very point, what will happen? So there will be nothing that will leave this kind of surface, r equal to 2 mu. For this very observer, so they will always take how much time? Infinite time. That means, so it will be never observed by this observer at infinity. Such, okay, so in that context, we call this r equal to 2 mu as an event horizon. Okay. So it is in this very context. So it will, if you see that, okay, for this very observer, it appears that what? From this very surface, if you are having any kind of radial motion of the, let's say the photons, okay, since they will take the infinite amount of time to reach this very observer, okay, so in other words, it will never reach to this very observer. So how it will look like? Nothing comes out of it, is it? So it will look like as a black, that's why we call it as a black hole. हाँ वो मैं समझाऊंगा. Okay, so वो मैं end lecture पे समझाऊंगा वो कैसे ली है. तो समझ आओ? So we will deal it in more detail. This is an idea of a black hole. समझ आओ? So for the time being, just see, okay, just relax. So you can say there in the Schwarzschild geometry or the Schwarzschild space-time, we are having a surface r equal to 2 mu, okay, which is not crossed by an observer, okay, or for an observer who is sitting at the infinity, it takes an infinite coordinate time for an observer to cross r equal to 2 mu for this very surface. Let's put it more in a more good way. Okay, so for an observer, it takes an infinite coordinate, for an infalling observer, it takes infinite coordinate time to reach this r equal to 2 mu surface. We call this r equal to 2 mu surface as an event horizon of the Schwarzschild geometry or the Schwarzschild space-time. Clear? But in reality, this is not actually a singularity. Samajh? Because the proper time taken by this infalling observer is a finite quantity when it crosses r equal to 2 mu. And one more point is that since our analysis, we are doing the solution of the Einstein equation outside r equal to 2 mu. Samajh? So we are not bothered about what r equal to 2 mu or r less than 2 mu here. Got it? Okay. So samajh aaya? Clear? For the time being, we will restrict ourselves to what? R greater than 2 mu. Clear? Okay, r less than and r equal to 2 mu we will take later on. Okay, in the next lecture. Okay. So now let's ask the question. Okay, so let's ask this very question. Suppose, okay, yes, I am an observer here and I will drop a ball from here, or this very brush from here, okay. So at this point when it reaches to me, so I ask what is the velocity at this very point. From Newtonian mechanics, what you will do? You will equate the kinetic energy at this very point to the potential energy. So it will be simply V equal to root of GH. So that will define your velocity. Now in the same way, let's say you are having a stationary observer, okay, in this very geometry outside r equal to 2 mu, okay, and you ask a question, there is a infalling observer or infalling particle, and once it crosses you or this very observer who is stationary, and he wants to measure what is the velocity of this very object. How much velocity it has. Okay, so let's pose this very question. What velocity as stationary observer at r, let's say, measures for the infalling particle as it crosses. Okay, so let's try to calculate this thing. Okay, so to have the solution, so I require actually the Schwarzschild geometry, is it? Okay, so we have coordinate time, let's say dt related to the proper time, dt prime, okay, for stationary observer at r, like this thing, dt prime is equal to 1 minus twice mu by r raised for half v. Because you are having the matrix contains, okay, so if you look at the line element, that is, what is the line element? ds square is equal to c square dt square 1 minus 2. Okay, so when you take the proper time, that you have to take the root of this very object. So So that will be root of. Clear? Okay. So now what is the radial coordinate separation? Also, okay, a radial coordinate separation. Separation dr corresponds to a proper radial distance. Radial distance dr prime measured by this observer. Which observer? Who is stationary, eh? Who is at rest? Suppose I am at rest in this very geometry and the particle falls by, okay, and I have to measure the velocity of that very falling object. What I have to do? I need to calculate what is my proper time and what is my proper distance at that very point. Samajhan? And at that very point, then I will calculate the velocity. Samajhan? Okay. Station by this observer. So how much is that? Anybody? So that is simply dr prime 1 minus twice mu by r raised power minus half, because it contains minus 1 power. So therefore we can calculate the velocity. So therefore velocity of radially infalling okay observer as measured by stationary observer. I should say infalling object or infalling particle, because that. So stationary observer at r is here. So how much is that? That will be simply dr by dt. Let dr prime. So this will give me the proper velocity. Yeah? So Samajhan, is that true? So how much is that? So just divide the two. So it will be simply 1 minus twice mu by r raised power minus 1 dr by. Clear? So what this dr by dt is? We have just calculated it. Dr by dt is actually equal to dr by d tau by dt. Okay? So how much is that? So it is 1 minus twice mu by r raised power minus 1, and it's actually equal to minus twice mu c square by r, is it? Raised power half into 1 minus twice mu by r. So this is raised power 1 and this is raised power minus 1. So they will add to 1. So much over? Clear? So what is our velocity? So therefore our dr by dt prime is equal to minus, okay, twice mu c square by r. This is valid only for what? So now what happens at when it approaches r equal to 2 mu? So let's look at. So what happens to this very velocity when it approaches where? R equal to 2 mu. That means once the particle approaches this event the horizon. So what happens? Anybody? So let's say as r approach to 2 mu, what will happen to this thing? So this r and 2 mu will cancel, is it? So therefore this dr by dt prime is approaches actually minus c, is it? So that means it approaches velocity applied. Minus is a sign for the infalling observer, okay? So in other words, let me take the magnitude of this thing here. So it is simply the velocity of light. Okay, so that means for an observer when he looks at this very particle crossing this, reaching this very surface, it's crosses at what velocity? At the velocity of light. So Samajhan? Do you think there is a problem? Huh? Do you think? Do you think is there a problem? The problem is here, since our solutions are valid only for what? R greater than 2 mu. We are not looking at what? r equal to 2 mu or r less than 2 mu. समझ आवा? Clear? Okay, so this is all analysis for the massive particles. So let's do it for the photons. Okay, let's look at how the photon trajectories look, because what we want to do to construct a space-time diagram, okay, or to construct the light cone structure of the photons. Because if I know the light cones, how light cones behave, within the light cone there always follows a trajectory of a massive particle. Okay, if let's think in terms of the special theory of relativity. Let's say this is a light cone. Let's take only the forward light cone. What is the trajectory of the massive particle or the particle carrying mass? So that's always within this very object, is it? It's not here, neither here. So that always follows the forward light cone. Okay, so if I take the backward light cone as well, so this is actually the trajectory of the particle. Clear? Samajh? And this is actually the trajectory of what? So the surface of this very cone. So this describes this describes what? The trajectory of the photon. Samajh? If I know these kind of trajectories, how these trajectories behave in this Schwarzschild geometry, I can then guess what is happening to these photons. Samajh? Or in other words, if I can construct the light cone structure, that means I have constructed the geodesics for what? The time-like geodesics. Because the time-like geodesics follow what? The trajectory within the cone. Samajh? Time-like geodesics are within this very cone, and you are having null geodesic like this. Samajh? Let's look at what happens to the light when it passes through this very geometry of this very space-time. So let's look at what I mean by the radial motion of the photons. Okay? So first we will get the geodesic equation for the photons, how they look. Okay? Then, so I will take 10 more minutes. Let's look at the trajectory of the photon. Okay, so first point is that we cannot use this proper time tau cannot be used. Our proper time tau cannot be used as a parameter. However, we will use affine parameter, because along the null geodesics, the tangent is always parallel, is it? It is all the tangents are orthoparallel to each other. Clear? So what is the parameter to use? Affine parameter. That I told you. Okay. So however, we use some affine parameter. Can you tell me why we can't use parameter? Think over it. I have told you many times why we can't use this tau as a parameter specifying the trajectory of the photon. This I have told you many times, but look at your notes again, okay, and think why. Yeah? Samajh aao? So what is our geodesic? So we are having null geodesic. So what is the null geodesic? So I can write it as Gij dx, okay, I dx j, that's equal to 0. Or in this way, so I'll write Gij x dot I in terms of the velocity, x dot j, that's equal to 0. Is this the null geodesic? In terms of this dots here does not mean differentiation with respect to tau, it means differentiation with respect to sigma. Okay? So let's write now this geodesic. So what is G00? G00 is, so it will be like this. C square 1 minus twice mu by r, then it will be T dot square plus 1 minus twice mu by r G11, that's raised power minus 1, then it will be r dot square. Okay? Because x dot 1, it will be r dot 1, r dot, okay? Plus r square phi dot square, that's equal to 0. So we are in the which plane? So by the way, we are actually in theta is equal to phi dot. So that's why I will not take theta coordinate here. Okay, and we are having other equations also. We have already derived those equations for t and phi. Now कौन सा क्या बेटा? Okay, so we also have 1 minus twice mu by r t dot, so that's equal to k. So let's call this as 1, call this as 2, and you are having r square phi dot, that's equal to h. Okay, let's substitute third and second, okay, for t dot and phi dot in this very equation. Okay, using t dot from equation second and phi dot from equation third in equation 1. So what you get? Almost we are done. We don't need to take extra time. So what we get? So we get this thing, this very equation. So this is the equation: r dot square s square by r square 1 minus is equal to c square. So this is the equation which will help you to understand the radial motion of the photons. So, and what is the difference with respect to the massive particles? There were an additional term is not there, that 2 gm by r, is it? And minus 1, k square minus 1. So, okay, so now let's take the radial motion. Radial motion of photons. So this describes the radial trajectory. Okay, or in other words, it is the energy equation of the photon. So, so now when I take the radial motion, so what happens to this thing? So my phi dot is equal to 0, because we are considering at now the fixed phi. So you are having this very mass. So this is the mass. So this is the radial motion. Okay, so you take, now theta is also fixed, we are actually here in the equatorial plane. Now you take actually phi is fixed. So you choose one point, one angle, okay, at that very angle you throw this very photon into this geometry or in this very space time. When phi dot is equal to 0, let's look at equation 1. Okay, therefore from equation 1 we have, so this is the important equation what we have. So it is minus c square into 1 minus twice mu by r t dot square, clear? Then plus 1 minus twice mu by r raised power minus 1 r dot square is equal to 0. Okay? Okay, so can you tell me what is this dr? Okay, so you can take that on this side, this very object you can take on this side, then what you will be having? Like this thing, r dot by t dot whole square. How much is that? What is it? Just tell me.
C square 1 minus 2 mu.
Yes, it's c square into 1 minus twice mu by r square. Clear? So in other words, what is r dot? It's dr by d sigma. What is t dot? dt by d sigma. So I can simply write dr by dt is equal to plus minus c, okay, 1 minus twice mu by r. Since we are dealing with the ingoing photon, so plus means the outgoing photon, radially outgoing photon, and minus means the radially ingoing photon. So we'll be take minus sign for radially ingoing photon. Okay, so which implies dr by dt, so that's equal to minus c into 1 minus. Or in other words, we can take both. For the time being, let's fix, okay, so let's keep it as such. So it doesn't matter. Okay, so what is the solution? First, let's write. What is the solution? Can you tell me what is the solution of this very equation? So you need to integrate it out. Okay, take t here, this on this side. So it is actually 1 by r kind of thing. What is the integration of 1 by r? So integrate. So that's log of r. So this equation, let's say 2. Integrate this very equation. Integrate this equation. Okay. So what I get? Rather the above equation. Sure, which is having plus and minus. So integrate this very equation. Call this equation as 2 and integrate equation 2. Okay, so I'll get Ct is equal to r plus twice mu natural log of r by 2 mu minus 1 plus constant of integration. Then I will write Ct equal to minus r because of that minus c. Yeah? So I'll be having two solutions because it carries plus and minus. That's why I will put that minus here. Huh? Plus some constant. So let's call this as third and call this as fourth. Now let's look at the structure. Okay, first tell me if I change in these very formulas, let's say in these formulas, let's change t to minus t. So this is actually which photon? What is this photon? Huh? Because this carries the plus side, is it? So it is a solution of the, so this is our outgoing photon. Okay? So what is this photon? So it is ingoing photon. Now let's change t to minus t. If I change t to minus t, okay, in this very case, so what happens? So outgoing photon becomes the ingoing photon and ingoing photon becomes what? Outgoing photon. So that means there is this symmetry maintained. Or so implies outgoing photon, outgoing and ingoing photon, ingoing photons interchange the trajectories because they specify the trajectories of ingoing and outgoing photon. Now let's say if I take r tends to infinity. So when I am taking r, so this is our radial coordinate, is it? So radial coordinate, let's take this radial coordinate to infinity. What does that mean? So that means it specifies me an observer where? At infinity. So when I am having an observer at infinity, what kind of geometry it will give me? Simple Minkowski space geometry. So there it will be simply the special theory of relativity. So what are the slopes then? So dr by dt will give me the slope of an ingoing and outgoing photon. What will be that? That will actually plus minus 1. Let's say c is equal to 1. So let's draw that. Okay, so let me draw it this way. So I'm sorry, okay, so first point is that when r tends to infinity, that means where we are looking at this photon. So this photon is observed by the observer where? At infinity. So that means, so the slope of trajectory for ingoing and outgoing is minus plus 1 because ingoing is minus 1 and outgoing is plus 1. Samajh aawa? Got it? Because it will be simply plus minus c. So what does that mean? Suppose at infinity, let me draw. This is our, let's say it is r equal, I will draw the full diagram. Let's say it is at r equal to infinity. So what will be the slope? So plus 1. So like this, it's at 45 degree. It's at 45 degree like this. Okay, so this is our outgoing photon. Okay, and this is what? Ingoing photon. Because this has slope minus 1. So samajh aawa? So this is our what? Light cone, the forward light cone. It means all the time like trajectories are where? Within this forward light cone. Samajh aawa? Okay, so this is at r equal to infinity. It means I am having simple Minkowski space structure. Now if you look at the form, okay, so let me write that formula again. Dr by dt That's plus minus c into 1 minus twice mu by r. Kind of thing. Okay. So now when r goes to the finite values, what happens to the slope? Slope. Now the slope increases. Is it? Is that true? So in other, okay, so this way. So let me put this way. So this is r equal to infinity. When you move towards the finite r, let's say, so what will happen to this light cone? It will shrink. Is it? It will be like this thing. Clear? So this will be actually these are the outgoing and ingoing objects. So let me draw the diagram now. So let's call this very surface. So we will write it this way. So this is our r equal to 0. So it is which diagram? CT and R. So this is R. So I am taking now here. So let's take this equal to R is equal to twice mu. So our horizon. So clear? So let me draw here. This is R equal to infinity. So at R equal to infinity. So what I am having? So this is actually our. Let me draw it this way. Then I will draw a good diagram. So this is which radially outgoing photon, okay? A radially outgoing photon, and this is radially ingoing photon. Samajh? Now when this photon enters into this kind of geometry, what will happen to this thing? It will shrink. It will go like this. What happens to here when it reaches? So it will become infinite. So that means this light cone closes up. Huh? Yes? Huh? Where? No, it will close up like this way. So although it will close up at this very, I will not be bothered about this very region for the time being. Clear? Huh? So that's what I am going to explain. What does that mean? I am going to explain in a moment, no issue. So I am just giving you actually first this space-time structure, okay? Because when you do the space-time structure, you always do it in terms of the light cones, is it? So when you know the light cone, how light cone behaves in a given space-time, you know actually the trajectory of the massive particles, how that will behave. Because the trajectory will be within this thing. Isha? So trajectory will be here. Got it? So let's draw a neat and clean diagram. Another, okay, in the another way around. Okay. So it has a very, it's a very significant diagram. Okay, so let me draw this way. Okay, everybody has drawn this thing. So let me now erase them. So let me fix a observer here. So let's say this is our stationary observer. At this very point, R is equal to some R, capital R. This is our stationary observer. Okay? So now at this R equal to R, you drop some object, is it? Samajh? Whatever analysis we have done till now, what we have observed? The observer who is sitting at infinity is not able to observe the particle to reach R equal to 2 mu, is it? That we should be able to show by a diagram. Okay? Samajh? It has a name to this way. It has very importance, sir. Because if you look at this very diagram, it gives you only the part of the space-time, R greater than 2 mu. It does not give the space-time R equal to 2 mu or R less than 2 mu. Okay, so this diagram gives you the problems with the coordinate system you have chosen. Okay, so we will go in the next lecture the different kind of coordinate system. You will see actually we will be able to cross this very region in that very coordinate system. Okay, and when we will look at some more general kind of coordinate system, you will understand those kind of wormholes. So the trajectory is connecting the two black holes kind of thing. Okay, so it is actually the how you choose the coordinate system. All the coordinate systems does not give you the complete information of a given space-time. Okay, you think it this way. So there is another way to think of you. I give you a sphere, is it? So everybody is asked to figure out a chart for a given location, or let's say for a sphere, part of the sphere. None of you will come to the same conclusion. Okay, think of the maps, different kinds of maps. You do not agree upon the maps. Okay, so much, or we call these as the coordinate charts. Forget about those things. Okay, so let's say a particle, you are having a massive particle that you drop from this very region at r equal to r. So much, what will happen? It will follow a time-like trajectory. So much, so let's write that very trajectory. Let's call that. So okay. So it will follow. Let's say this is the trajectory that will be followed by this kind of particle. So much. So it's an infalling. You should not say in the diagram it looks like this. It's simply an infalling observer. So on this diagram it's like this. So let's say this observer radiates a light, a photon, okay, and it's observed. This photon is observed by this observer. That is how he can measure where the particle goes. So let's say I am here, okay, or you send somebody to some another galaxy, and he will be continuously radiating a photon, okay, to track him down. So the same thing is here. Let's say he radiates a photon. Okay, so what is the trajectory of the photon? What is the trajectory of the photon? So it will be a null trajectory, correct? So let's say it emits a photon here, so it is something. Let's say here, so you are having a light cone and event. So this is the point where, so this is the light cone structure of what? Your stationary observer, because it goes through this thing. So this is the point at which the observer observes the light, this very signal. Okay. So now what happens? So the moment it goes towards r equal to 2 mu, what happens to the light cones? They shrink. So what will happen to the light cone here? So it shrinks. So that means the amount of time this will take to reach this thing will be larger than this thing. So here it will shrink completely when it reaches to where? R equal to 2 mu. So what is the what will be the velocity? It will tend actually to c. So that we have seen. Or in other words, the slope here will be infinite. So in other words, when the particle reaches to r equal to 2 mu, the amount of coordinate time that will be observed by this observer is infinite. So for this very observer, this will never reach to this very region. So what we have done analysis mathematically, we are here on a diagram. Because diagrams are very useful to understand things. Clear? Okay, so these diagrams are usually known as Eddington diagrams. He is a well-known cosmologist.